welcome back to my 6 day of the NPTEL lecture session. Today I am Prahlad, and today we will do some uh, assignment solution of assignment 5 solution of the assignment 5, and we will discuss some more about the interpretation that we are have discussed in the class in class. So from the week 1 to week 5, week 4, we saw that there is so many derivation regarding how this excitation de-excitation is happening, and after that we found that there is some two different coefficient that constant that are derived by Einstein, which says that there is a relationship between the spontaneous emission and simulated emission. So from and we found that both the constants depend on the transition dipole moment integral, transition moment integral. And the relationship between spontaneous and simulated emission is depends on the energy separation of the two states. So with this, the week 5 is much more interpretative and is much more focused on the what we see in real time of real experiments. So based on the idea that we gather from week 1 to week 4, we will use that idea to much more experimental and derive some equation, and we will see what we get the equation, what we get the expression of absorption, emissions, and TK. Okay, and after that, at the end of the class, end of the lecture session, what we see that there is a attempt to derive the selection rule based on only rotational levels, and in the next week there will be something from vibrational levels and all. So let's start today's session with using some starting from the Einstein's rate coefficient equation, Einstein constants, and we will do the derivation. We will do the assignment solution one by one. Okay, so let's start. So beforehand, I just need to share my screen. It is visible. So let me start now. Okay, so what we found that if there is two state, some state I to state F, then if we excite by light h nu, where nu is the difference between F and h nu is the difference state, then there is a two different pathway that molecule can relax back to ground state. This is simulated emission, and another is spontaneous emission. Everything is same color. Okay. Now, so A is a rate constant for spontaneous emission. So what we found, the B rate constant for spontaneous emission, simulated emission as well as simulated absorption, is nothing but okay, and the relationship between A and B nu cube. Okay, so A will be which is nothing but 2 pi nu cube by C cube. So what we see, A and B both are proportional to the transition dipole moment integral. So now these are the expression of A and B, but how to measure A and B? So to measure A and B, so for it so to how we measure A and the expression of A, so we can do some experiment where for a molecule in, let's say, in one state and this molecule in excitation is 2, so population of in one state is n1 and second state is n2. Now at time t is equal to 0, all the population will be in state 1, but once we excite it at time t, then few of the molecule, if we say the x amount of molecule is excited, then n1 minus x amount of molecule will be in ground state. Now after the excitation, to state 2, switch off the light. Then what will happen? Molecule will decay exponentially. If you record spectra, you will get a exponential decay of population. So that means this follows first order kinetics. So if we write the expression of change of population of excited state, population of excited state 2 after switching off the light, it will be nothing but like this, so to n2, and the proportionality constant will be A, as we mentioned earlier. So if we integrate it, then what we will get? N2 t star exponential A into t. Now t star means when the light is okay. So if we think like this, then A represents so this this thing is nothing but 1 by A. So this is the lifetime of the excited state. Now, as we mentioned, the expression of A is nothing but 2 pi nu cube 3 epsilon h c cube for 1 to 2 transition. We can write it 2 mu z e 1 square. So the lifetime of state 2 is proportional to 1 by nu cube, rest of the things are constant, and 1 by so lifetime of a excited state depends on the energy gap and the amount magnitude of transition dipole moment. Okay, so with this we can look at the first question of the assignment 5. Consider a So consider a system that I mentioned previously, state 1 and 2 with a population n1 and n2 respectively at time uh, t0. Okay, in presence of light. After switching off the light at the time t is equal to t, which of the following is our correct statement with respect to population decay of the excited state? So what we see, the population decay is follows the first order kinetics. Okay, so so in the decay profile you can see there is no incorporation any radiation density. It's a spontaneous decay, so radiation density is not incorporated with it. So this is an incorrect statement. Now rate of population depends on n1 and n2. Okay, rate of population doesn't depends on n1. Okay, rate so this statement, this is an incorrect statement, but depends on n2. Okay, the rate of the population decay depends Einstein's coefficient. Yes, because dn2 by d2 is nothing but a into n2, and n2 is correct answer. Now population decay, as we mentioned, it follows the first order kinetics like this. So this is also a correct option. Okay, so now let's look at the second question. Screen it not visible. Wait. Is it visible now? Hello.
Yes, sir. Now it is coming. Yes, now it is coming.
Okay. Can you hear me?
Yes, I am hearing.
Okay. Okay. Now, question number 2. The system the described system at question number 1, they said that what will be the what is the information which is correct for the lifetime. Okay, so lifetime of the excited state. Anyway, so as we see that the lifetime the decay of excited state excited state is follows the first order kinetics. So we can tell that from our knowledge of chemical kinetics or from a mathematical derivation, the decay of lifetime of excited state is defined as the time at which the population of the excited state n2 decreases to 1 e by of the n2, which is straightforward. That is correct one. Now the decay lifetime tau is of excited state is directly proportional to the Einstein's coefficient. So what we found that n2 at t is n2 at t tau exponential minus of at. Now if we write something like this, so tau is your lifetime, therefore tau is 1 by a. So tau is not directly proportional, it will be inversely proportional. Okay, so this is an incorrect option. Okay. Now stronger the transition, but and if tau is inversely proportional to a, then we can write proportionality constant so this is somehow connected to the transition dipole. So this is also inversely proportional to the modulus of a transition dipole. So total statement is incorrect. Now stronger the transition, greater is the decay of the tau lifetime tau of excited state. So stronger transition means, so stronger transition denoted by if the magnitude of this increases, then if this term goes up, I increases, then your lifetime will decrease. So for strong transition, lifetime will decrease, not increase. Okay, so transition magnitude will decay. Okay, so this is incorrect. Now larger the separation of the states, smaller is the decay. Okay, so let's say a system of A the separation between two states is mu A. Now think that in somehow I can stable the excited state. Okay, so now the is goes down by nu prime. Okay, so both are the same molecule. Okay, so you can think like that your excited state is polar in nature, and you introduce some polar solvent, and polar solvent will most stabilizes your excited state, and therefore your energy goes down. But the system is same. Therefore, this term remains constant. So, the lifetime of state 2 is, as I mentioned previously, is depend on the separation between two state and the magnitude of transition. Now what I say, this is remain fixed. This is remain fixed. So transition the lifetime will only depend on the separation between two state. Now in this case, what we found, nu A is greater than nu. Therefore, tau A will be less than tau A prime. So if the separation between state 1 and state 2 increases or decreases, then the lifetime will be decreases or increases. Okay, so larger the separation, smaller will be the decay of the lifetime of the excited state. That is the correct option. Okay, so now, so with the idea of whatever we derive in the first 10-20 minutes, we can able to answer the first two questions. Now let's look at the third question, which is based on the date of transition. So question number 3. Correct expressions for the relation between rate of absorption and absorption coefficient among the following is are. A, Okay, so let's derive that. So there is a term that we can see in this question is intensity. So let's talk about the intensity, how it's coming. So for that, I hope everyone knows that what is Lambert-Beard law. What it says, if a light pass of intensity I0 pass to a medium of optical diameter L and concentration C, the intensity will decrease due to the absorption of light, and the relationship between the two incident intensity and after absorption will be like this. So now if we take this thing as a differential form, okay, so it's nothing but I is equal to I0. Okay, let's take this a ln. So the differential form will be so dx is nothing but different minus x to x. So this is nothing but L or dx. If you integrate it 0 to L, you will get the value of L. Now on the other hand, so intensity on going to I to F state is also depending on number of molecule in the per volume. Okay, number of molecule present in per volume of the substance, and frequency of the light, energy of the light or whatever, and rate of transition. Okay, now if we equate both of them, then what we get, so omega WFI is equal to 2.303 C into I N H nu. Okay, now C is the concentration which can be read molar concentration, which can be written as like this. Okay, so rewrite these things as 2.303 mu N I N A N H nu. So N will be cut, and then what we will get, the expression is something like this. So this is an expression of 2f. So let's see if it is there or not. So first option is given there is actually the correct one. Now here you can see that two different term is coming. One is U and another is refractive index, that is eta. Okay, and there is another thing is integral, so we need to derive it more. So now if we look at the intensity is nothing but U into C by eta, where U is the total energy density. See here, this is concentration, this is speed of light, be careful, and this is refractive index. So your WA5 can be written as 2.303 into U into C by eta. Okay, so your option B is also correct one. Now total energy density is nothing but the integration of radiation density. So U can be written as radiation density का integral. So WA5 so taking all the new dependent part inside the you can take that new is density. So this is the final. Okay, so this is the final expression of the rate of transition from I to F. So this doesn't have the radiation density part, this is a radiation density part, this is the correct option. Okay, now moving to the question number 4. Which of the following are correctly describing the relationship between absorption coefficient and Einstein's coefficient A and B respectively. So what we left from last derivation is WFI is nothing but 2303 CNAH this is rate of transition from I to F. So this is somehow proportion to the rate constant, Einstein rate coefficient into radiation range. Okay. Now, so we will get the expression of B. So B is now if we know A, B, then we can easily get B. So A by B is correct one. Okay. So your expression of A is this. So no, we can remove one of this. So expression of so this is the expression of A and this is the expression of B. So both of them doesn't have any rad nu. So option A and B are not valid. Incorrect, incorrect, and as well as this is also incorrect. So there should not be any rad nu part in the radiation in this coefficient in A and B part. So the correct option is nothing but C. Okay. However, if everything is looking good, for a trick can be done, that is A and B should be if we get the expression of for both A and B in 4 different options, then it can be checked whether A by B is equal to 8 by H nu by C cube, H nu cube by C cube. But you should, but be careful, there should not be new rad nu term in the equation or anything else. Okay. Now question number 5. The correct statement. Natural line with so till now we are discussing about the absorption profile, like this thing. Now questions comes now is about the shape of the light, shape of the absorption. So for that, for a natural line with the, if we, the excitation between state I to F or 1 to 2, the natural the intensity is depend on where tau is a lifetime, then the natural the intensity can be written as a Lorentzian shape. Okay, so which is nothing but I max so Lorentzian function is nothing but Fourier transform of the exponential function. So if we look at the the graphical view of the intensity, so at central frequency omega 0, this will be the I max and this is the line shape. So this is for I max. So the term now coming is FW HM, that is means full width at I max by 2, half of the maxima. So this is something nothing but like this area. Okay, so this is full width half maxima. So Lorentzian distribution, the full width at half maxima, which is denoted by this thing, is nothing but 2 pi d nu half, which is nothing but tau inverse. Tau inverse is nothing but the A. Okay. So what the questions are saying, the natural line width of spontaneous decay is described in terms of Lorentzian function. So this is a correct one. Now the full width at half maxima of natural line width is spontaneous decay is equal to the lifetime of the spontaneous decay. As I mentioned here, is not equal to inverse of the lifetime of the system. So this is a incorrect. Now the full width at half maxima of natural line width of spontaneous decay is equal to the Einstein's coefficient. So this is the expression. So this is a correct one. And the last one, the natural line width is purely described by the intrinsic behavior of molecule without influence of any external factor. Okay, so this is a correct option. Now so natural, it is called natural line width because the system is not feeling any what I can say, any influence or any broadening due to the environment. If it face any influence of the system, another system present on influence of another external factor, the peak will not show like Lorentzian function. It will show like a Gaussian function. So natural line width, you can say, is a isolated absorption profile of a molecule. So it is nothing but a due to the intrinsic behavior of the molecule. Okay, so these are the first 5 questions. I just take a 5-minute break and after that we will continue. let's start. So question number 6. This spectral line shape is given by a Gaussian function So as I mentioned, the natural line width is coming from the Lorentzian shape. Now, if there is some heterogeneity, means Lorentzian is a homogeneous system. Now, if heterogeneity introduced in the system, now it's no longer Lorentzian in shape; it will be a Gaussian in shape. So the first option is correct. Second option, what FWHM of the Gaussian functions is nothing but 2 into root 2, but there should be there is a sigma also, that is correct option. Now the d omega half of Gaussian distribution is smaller than d omega half of the Lorentzian distribution. If you look at the, so this is distribution, I can think, and this is a distribution of Gaussian. So you can easily understand that from same case the full width of half maxima here also little bit here, something here, So d nu half of Gaussian should be greater than d nu half of Lorentzian, because of there is an influence. There is an influence of external factor, and that makes the peak broadened. And next, the experimentally the experimental parameters such as Einstein's coefficient A can directly obtained from Ig omega. So this thing is not possible for from the uh, uh, from the intensity of from the line shape of the Gaussian function, because this the FWHM is now no longer depend on the lifetime. It's something depend on the standard deviation of the distribution. Okay, so now for only in natural line with case, that means isolated and homogeneous case, the A factor can be measured from the FWHM of the peak. Okay, so from Gaussian it is not possible. Okay. Question number 7. The transition moment integral TMI for a transition from initial state I to final state F is given by the correct statement among the following is or are the dipole moment mu contains only the permanent piece equilibrium geometry can be expressed as a Taylor series expansion. Now with this we come to a point. Now we have to look around how this term transition moment integral is related to the transition transition with the selection rule. Okay, so let's have a molecule A and B having dipole moment from here to here, and the potential energy curves look like this, and you can think the equilibrium geometry distances are 0. Then this is a state, this is also a state of AB. Now both the states are close to equilibrium geometry, so therefore for that you can see that the bond is little bit elongated. Okay, so the dipole moment, permanent dipole moment, is no longer the same, so mu can be written as linear combination of permanent dipole moment and some more factor, and that factor is derived using Taylor series expansion. And so on. So now if we think if we replace just think with a simpler version, that is a nothing but Taylor series expansion. This is permanent dipole moment, and there is some induced factor that is this, and if we are incorporate higher order term, you can use alpha, beta, gamma and all. And so on. So this is the expression of transition dipole. Okay, so now what it says, the dipole moment mu contains only permanent dipole term, so that is not correct because it has some influence of second order, third order terms, so this is a incorrect option. And as we saw earlier, it's you can expand it using Taylor series expansion, and which is known from the first class that if the TMI is 0, then the transition will not allow, so that is a forbidden transition. So option D is correct and this is incorrect. Okay, now we need to incorporate this mu term in a transition moment integral. So what we can write that TMI and so on. Now the thing is that how you can write the expression on I and F function. Okay, so for that we have to look out some few things, so that we all know. but what is the expression of H is not so common, not we explore properly. Okay, so this is nothing but, so kinetic energy of the nuclei, kinetic energy of electrons, potential energy or attractive term between nucleus and electron, electron repulsion, and there should be nuclear repulsion. The polyatomic polynuclear system you can think. So there should be nuclear repulsion term. Now just we need to solve this to get these things. So here comes von Oppenheimer. So you can see this is a big Hamiltonian equation incorporates kinetic energy of nucleus and kinetic energy of electron nucleus attraction, electron repulsion, nucleus repulsion, so many terms. So what von Oppenheimer did, so if we write a function like that, it will show this expression where En is the energy of the nth state. What von Oppenheimer did, it just segregate this nuclear coordinate and electron coordinate. However, electron coordinate is depend on the position of the nucleus. So now if we use this, and now if we write the TMI, this now becomes very big equation. And we know mu is also can be expanded as mu 0 alpha r beta r square and so on. It's a very big equation, so it needs some approximation to get the solution of the selection rule. Okay, so that will come later part. So let's do the second question number 8. So with this expression given in the previous slide, we have a question. So, as I mentioned previously, the psi E psi E and S under Born Oppenheimer approximation is segregated uh, into two different parts. One is nuclear coordinate, one is the electronic coordinate. So once what we see, the electronic coordinates, it not only depends on the coordinate of electron, it's also dependent on the nucleus also. So once uh, so nuclear coordinate evolves with vicinity of the electronic environment. Okay, so therefore the electronic coordinates is parametrically depends on the nuclear coordinate, but nuclear coordinates is doesn't depend on the this xn doesn't depend on the nuclear coordinate. So this is an incorrect one, but this is psi is obviously parametrically dependent on the nuclear coordinate. Now once we excite a molecule, what will happen? It will go to the excited state. Now the excited state is when it reaches to the excitation is nothing but the same nuclear configure, same nuclear distance from the nucleus, but the molecule will evolve to a stable position. That will not be a similar nuclear coordinate that it has previously. So therefore the option C is also not a correct option. So nuclear coordinate after transition may not be the same. Okay, if there are any question you can ask. And what the last option says, the nuclear coordinate can change as a result. That is the thing that I discuss here. So once we excite it goes to a state which is vertically upward from the current state, but what happens from there, it will roll down to the minima, and the minima structure is may not be the same nuclear coordinate. Yes. Hmm. That means the coordinate of electron is depends on the how the nucleus is arranged. Or see like that, you are exciting, the nuclear coordinates is changing, and on that vicinity the nuclear coordinate also changes. So it's not like that the relationship between the electron and nuclear coordinate has some dependence. Okay, it's not like the electron behaves freely than the nucleus. Okay, so there is a relationship which is nothing but that is denoted as a parametric dependence. So it has a dependency with the nuclear coordinate. Okay, so if you look at the big picture of psi En, then there you can see the the whole expression has of electronic of wave function has both the electronic part as well as nuclear part. Okay, therefore it concluded that the psi is a parametrically which is a wave function is for electron, which is also parametrically dependent on the nuclear coordinate. Okay, so many high level of quantum wave function based quantum mechanics book can show it like that. Okay, any other? Is this clear? The nuclear coordinates can change as a result of transition from one state to another. Yes. Okay, so this is very much needed if you want to do some nowadays this quantum calculation is there, no? So for that thing it actually works like that. You exciting so it's like a, if you know this vertical excitation, adiabatic excitation, and is actually depends on that. The vertical excitation is nothing but you are exciting at the same nuclear coordinate, but the molecule is not rest in that state. It should be rolled down to the at minima. So at the minima, after the transition, when you excite the molecule after the transition, when it reaches to the minima, the nuclear coordinate are not same. Therefore, the nuclear coordinate can change while the transition. Okay. So question number 9. For a diatomic molecule AB, the Hamiltonian can be expressed as a sum of kinetic energy if atom A of atom A kinetic energy of atom B and the relative bond energy of AB represented by U relative AB. Then when the molecule AB is considered as rigid rotor, the correct statements among the following the separation between always fixed the units what is rigid rotor? So if you take AB as a molecule and if the bond length between these two are fixed, then this is called rigid rotor. Now the rotation along rigid rotor like this, so that the center of mass should not change. It can be out of plane also, like that and like that, but the center of mass will not change. Okay, so the what they said, for a rigid rotor case, the Hamiltonian of tube system can be written as now this part is actually depend on three factors: electron nuclear the potential, but electron nuclear attraction, electron repulsion, nuclear repulsion. Now this also depends on the as the R is fixed, therefore this whole term became constant. Okay, and the R is the position separation between A and B. Okay, not the separation between the two nuclear coordinate. Okay, because A and B is a nuclei. Okay, two atom you can take, but not the nuclear coordinate. Okay, and mu and the U relative AB is constant. As I mentioned here, this is constant, and this is for rigid rotor case. And in the next lecture you will see something which is known as vibrational motion. If a vibration in which the center of mass doesn't alter, then that kind of vibration will called a normal motion. Anyway, that will be maybe will be taught as next class. Okay, so these are the two for the question number 9. So let's do the last question of the session. Okay. For a molecule AB described in question 9 under rigid rotor approximation, the Hamiltonian can be expressed as So in rigid order approximation, the HRR is nothing but for two systems with some constant term. Now think like this: this molecule A and B is here, a separation. This is a mass Ma. Please wait. So this is the distance, that is R internal, and if there is a center of mass, and this distance is center of mass. If the two mass are same, and therefore their distance will be same. Now if we rather represent with respect to this in this form, Cartesian form, we can represent it with respect to origin. So this is a distance from origin for B molecule, and this is for A molecule. Okay, so now if we represent it with respect to center of mass, just do some coordinate transformation, then we can write two m delta square Cm h cuts by 2 mu delta nu square internal. Okay, so now Cm is the motion along center of mass. Okay, so along the center of mass, if it moves, it is very hard to trace, and that's why the translation motion along the center of mass cannot be measured using any spectroscopic method. So there is no spectroscopic method to determine the translation motion of center of mass. It's very impossible type of thing. So you can write this in terms only the internal coordinate. So where the internal coordinate is nothing but gradient along x, y and z. Okay, so now what does it mean by m? M is nothing but summation of two mass, and mu is a reduced mass, can be written as ma into mb by ma plus mb. Okay, so these are the things that are needed for the next class to derive the selection rule for rotational motion. Okay, so the first thing is the mu is a reduced mass, and the sum of reduced mass is okay, but not the sum of the mass A and B. The center of mass changes when a molecule undergoes rotational motion. As I mentioned, when in rigid order approximation, when molecules undergoes rotation, there should not be any change of center of mass. The separation between A and B can be represented as internal coordinate that I mentioned over here. The separation between A and B can be represented as the internal coordinate. And the last option, the center of mass remain fixed when the molecule undergoes the rotational motion. Okay, that is the part. With this, we are done with week 5 assignment solution, and week 6 we will see uh, how the selection rules of rotational levels are derived, centrifugal distortion, then where you can see that it is a special case when the rigid rotor approximation fails, and how the energy levels are separated, and some rotational constant and all in the next few lecture. Okay, with this I want to stop it now. If you have any question, you can feel free to ask. Yes. It, it is MSQ, only MSQ, like this. Whatever we are doing, there will be no descriptive question. You don't need to write anything. You just there should be is a multiple choice answers. Huh? I don't think it is means it it is. I think it will not show there. It's just only the previous year question will not be there. No, you can just do whatever we have done in class and go to the lecture, and it will be simple one. It will not be difficult. And I think it is a online mode exam. No. Okay. So you are not need to travel some place to appear exam. Are you? Okay. So anything regarding the class? Any dispute or any questions? Okay. So I am stopping it here. Thank you for joining. Okay. Bye.